Welcome to Electrical Circuits. We're going to add 7 items to our Physics Everything sheet today. Last week, we talked a little bit about static electricity, and static electricity is when charges are sitting still in an electrical field. Today, we're going to talk about electrical circuits, which is when charges are moving in a complete loop. And electrical circuits is what makes up most of our electronics. It's a series of circuits, and each circuit does something a little bit different. So let's start by adding the term circuit to our Physics Everything sheet. A circuit, its definition has 3 parts. Number 1, a circuit is a complete loop. It's a complete loop of conductive material. So a circuit has to go in one full circle or oval or square. The shape doesn't matter, but it does have to connect to itself. It has to be made of something conductive. So metal is usually pretty conductive. Paper, probably less conductive. So it does have to be made of something that will conduct electricity. And it has to be a complete loop of conductive material from one side of a power source, the positive side, to the other side of the power source, the negative side. So let's take a look at what that would look like. Here we have a little picture of a circuit, and I've labeled in a few different components that might go within a circuit. So here we're starting at a battery, and the battery has 2 sides. It has a long line and a short line. The long line is the positive side of the battery. The short line is the negative side of the battery. So from the positive side of the battery, I go around in a complete loop. The loop goes from the positive side of the battery all the way around to the negative side of the battery. And I'm assuming that this loop is made of wire or some type of metal, so it is a conductive material. So that makes it a circuit. You'll also notice that there's this other funny little squiggly circle thing as part of my loop, part of my circuit, and that is representing a light bulb. I could also have a little zigzag line that represents a resistor, or a circle with a line and a triangle inside of it. That could represent an LED bulb, or a bunch of other different components that you'll see as we add them onto our circuits. So a complete circuit is a conductive loop of material going from one side of the power source, the positive side, to the other side of the power source, the negative side. All right, there are 2 types of circuits that we're going to take a look at. The first of them is called a series circuit. So a series circuit is a circuit with a single path and multiple components on that path, each component coming one after another all along the same path. That would look kind of like this. So in here, we have a series circuit. And this series circuit goes positive side. You can see it's a single pathway. I never get a choice of where I go. I just have to stay on the same pathway all the way around. I'm going from the positive side of the battery, the long line, and first I go through a light bulb, then I continue and I go through another light bulb, and then I continue and go through a resistor, and then I go through a third light bulb, and then I end up back at the negative side of the battery. Or I could go backwards from negative to positive, doesn't matter which direction you're going. But either way, there's a single pathway, and I go through multiple things on that pathway. We call that a series circuit. It's a series of items all in a row on the same circuit. Okay, our other option is a parallel circuit. A parallel circuit is one with branches, and each branch has a separate path for the flow of the charge or the flow of the electrons. So you know that it's a parallel circuit if you have a choice of which path the electrons or the charge is going to travel on. So here's an example of a parallel circuit. Again, I start from the positive side of the battery, the long side, and then I go to here and I have a choice. I could either go down and go through this bulb and then go back to the battery, or I could keep going and I could go to this junction, and then here I have another choice. I could go down and through this bulb and back to the battery, or I could keep going again and I could go out and I could go through this bulb and then back to the battery negative side. So I have 3 pathways, 1, 2, 3. Each of those pathways has a resistor or a component on it. In this case, it's all identical bulbs. And they are running in parallel with each other, meaning I could go through one of them, or I could go through the other one of them, or I could go through the third one of them. But I have a choice with the current which pathway to go on, and that's what makes them parallel circuits. Okay, so when we are calculating the resistance for a series and a parallel circuit, I'm actually going to introduce the term resistance first, and then we'll come back and we'll talk about how to calculate the resistance for series or parallel circuits. So there are three components that go into a circuit. First, you have the resistance of the circuit. We're going to represent that with a lowercase r or a capital R, but an R of some kind will represent resistance. Then you've got the voltage of the circuit, represented with capital V. And then finally, you've got the current in the circuit represented with I. All right, so resistance is the amount the current is slowed down or resisted as it goes through an obstacle. So every time the current goes through a component in the circuit, it's going to be resisted in some way. It'll slow the current down a little bit. The voltage is the potential energy difference from one side of that component to the other side. So voltage is an energy drop. You can sometimes call this the drop or the energy differential. And then finally, the current is the flow of the charge or the flow of electricity through the circuit. So this would be like how many electrons are flowing and how fast they are going. All right. We represent resistance is represented by with the variable r, and we can use ohms, which we show with a funny-looking horseshoe, as the variable. That is the Greek letter omega, and it's like upside-down horseshoe, and it stands for ohms. Voltage is represented by the variable V for volts, and current is represented by the variable A, which stands for amps, which is a shortening of amperes. So current is represented in amps, voltage in volts, and resistance in ohms. There is an equation that relates these three things, and that equation is V equals IR. We call that Ohm's law. Voltage is equal to the current times the resistance. This is really similar to a lot of other three-variable equations like F equals ma, solved in really similar ways, but in this case it's representing the potential energy difference, which is the voltage, the current, and the resistance through a component or through a circuit. All right. Now I'd like to go back and talk about how we calculate resistance, because one of the first things you're going to want to do when you have a circuit is figure out the resistance, and the first piece of that is figuring out whether it's a series or a parallel circuit. So for a series circuit, when calculating the resistance, it's real easy. You just add them up. So for my total resistance, that's going to equal the resistance of the first component plus the resistance of the second component plus the resistance of the third component. Looking at our series circuit example up here, my first component would be this one. So let's say each bulb has a resistance of 1 ohm, and the resistor is going to have a resistance of 2 ohms. So I'd have 1 plus 1 plus 2 plus 1. 1 plus 1 plus 2 plus 1 gives me a total resistance of 5 ohms on my circuit. For parallel, calculating the resistance is a little bit trickier because we calculated it inversely. So when calculating the resistance for a parallel circuit, 1 over the total resistance is going to equal to 1 over the first resistor plus 1 over the second resistor plus 1 over the third resistor. So again, if we say each bulb is equal to a resistance of 1, it would, in this case, be 1 over 1 plus 1 over 1 plus 1 over 1 equals 1 over x, 1 over my resistance. So 1 over 1 is 1, 1 over 1 is 1, 1 over 1 is 1. I should have used a different value other than 1, but that's a total of 3. 3 equals 1 over some number, and in order to find that, I would have to invert it. So 1 over some unknown number, and that number would be 1/3. 1 over 1/3 equals 3. So my total resistance is going to equal 1/3 for this circuit if each bulb equals 1. Let's show some other examples on how we would go about calculating there. So here's an example for a series circuit, and then we'll do one for a parallel circuit. There you go. So for a series circuit, if I have 3 resistors or 3 bulbs, the first one is 2 ohms, the next one is 3 ohms, and the next one is 4 ohms. They're all in series with each other. To find the total resistance, I just add them up. 2 plus 3 plus 4 is a total of 9 ohms. If those same bulbs were in parallel, then I would put them on the bottom of the equation in the denominator each time. So 1 over 2 ohms plus 1 over 3 ohms plus 1 over 4 ohms. Then I need to find a common denominator. Yay! Adding fractions! Everybody's favorite part of math. So the common denominator for 2, 3, and 4 is 12. That would give me 6 twelfths is the same as a half, plus 4 twelfths is the same as a third, plus 3 twelfths is the same as a fourth. 6 plus 4 plus 3 is 13 over 12, which is equal to 1 over the R total. This is the part that a lot of people forget, is setting it equal to 1 over R total. And then I have to invert those numbers in order to get R by itself. When I invert 13 twelfths, it flips upside down, and I get 12 thirteenths of an ohm is equal to R. So you'll notice when in parallel, I end up with a smaller total resistance. When they're in series, I end up with a larger total resistance than any of the individual resistors. So series, I'll end up with big resistances. Parallel, I should end up with smaller resistances, and sometimes some funky fractional ones. All right, so that is resistance, voltage, and current. The last thing that we're going to add today is power. Power we're going to represent with capital P. We may have already added power in a different context, but now we're going to add power electrically. So capital P stands for power. Power is the rate of transferring electrical energy through a circuit, and power is equal to the current times the voltage. Now, we can also come up with some other equations for power by inputting IR for V. So if I take IR and sub it in for V here, it would be I times IR. I times R is I squared R. So power can also be equal to I squared R. Or I could sub in voltage over resistance for the current. Again, that's doing a V equals IR, but solving it for I. And that gives me V squared over R equals power. The big one to remember is P equals IV or P equals VI. They're multiplied, so it doesn't matter which side you write it on. Power, the unit is going to be in watts. So if you have a 60-watt light bulb or a 100-watt light bulb, that's an indication of the power that it's using, how much electricity is being transferred through it every second. And watts is equal to a joule per second. So a 60-watt light bulb will use 60 joules every second that you have it on. Okay, so that is power, and you'll notice that power is a combination of the current and the voltage. So it's the drop or the potential energy difference and the flow of the current that kind of multiplied together give you the total electrical power that's being used. All right, so the last thing that I wanted to do is talk through this diagram of voltage, current, and resistance, because voltage, current, and resistance can be really, really tricky. So we're going to talk through one model of understanding what voltage, resistance, and current actually mean. So one way of thinking about voltage, current, and resistance is we can think about them as a series of vertical pipes that are different thicknesses. So these lines represent the current, how much water and how fast that water is going as it goes through these vertical pipes. You can also think of them as water slides or waterfalls. So in this case, we're going to have three resistors. We're going to have one resistor called R1, and that's going to be at the top up here. And it's in series with two other resistors, R2 and R3, that are running parallel to each other. So this is a series with a parallel. It's got a series and a parallel in it. In this case, the resistance comes from the pipe getting thinner. So in R1, the pipe gets thinner, and that means not as much water can get through it, and so that's going to provide some resistance. It's going to kind of slow things down. Then in R2 and R3, there is one really thin pipe. R2 is my thinnest pipe, so that's going to provide the most resistance. It's not going to allow as much water to go through it. R3 is a thicker pipe, so there's less resistance, which means more water is going to go that way. So current tends to follow the resistance. Here, if I do both of these lines together, so both of these lines would be coming through, and they're coming up, they're being pushed up, and this jump that they're taking, this vertical shift from here to here, is called the voltage. Remember, it's a potential energy difference. So the difference from the low to the high would be the voltage that the pump or the battery is putting onto them. So it's the voltage of the battery would be equivalent to the height up in this comparison. Then they go through the first resistor, and that second drop right here is also a voltage. So how far does the water drop in this case would be equivalent to the voltage. You'll notice that the total drop through this circuit that every piece of water has to do is going to equal the total height or the total voltage that it started with. So the battery pushed it up, say 3 inches, and then it went down 1 inch here, and then 2 inches here. So it goes down a total of 3 inches. And it doesn't matter which pathway it travels on, it still has to drop the same amount. So voltage is added together in series. You'll notice that the voltage is the same for both pathways when they're in parallel. So the height component here would be the voltage. Voltage up equals voltage down. In series, we add the voltages together, that plus that. In parallel, the voltages are going to be equivalent to each other. The resistance is based off of how much total piece here. Oh, and I'm showing that voltage difference right here. The voltage of the battery is equal to V1 plus V2, and that's also equal to V1 plus V3. So this plus this, or this plus this. All right. The current is equivalent to the flow. So how much this is moving around. So the current here would be the same through this entire section. And then right here, the current is going to split. So less current goes through the more resistant pipe. More current goes through the less resistant pipe. But the total current remains the same through the entire series. So things that are in series have the same current, even though the voltage splits or adds up to the total. In parallel, the current is going to split and add up to our total. So this current plus this current equals our original total current. So I took the length of this arrow right here, and if I split that length, it gives me a small arrow here plus a medium arrow here to equal my large arrow right here. This large arrow, this large current, split into those two areas. So in parallel, the current splits, but the voltage is the same on both pathways. All right, so the current here the current of 2 plus the current of 3 is going to add up to this current of 1 again, and then it flows back through the circuit. So that's one way, one model of thinking about voltage, current, and resistance. Another model that you could think about it is like the entire student body of San Marin High School running around the track. So the resistance would be like obstacles that are put in the way. If we put out a huge sand pit on the track, that would slow everybody down, and that would lead to more resistance. Or you could also think of resistance as the number of lanes that are open. If all 8 lanes of the track are open, then people can run around each other, and people are probably going to be running pretty fast through this circuit around the track. But if only 1 lane is open, then you're going to get a lot of traffic as people can't get by everybody. So then we're going to be going a lot slower if we have 1,000 or 1,100 people all walking in a single lane of the track going around. So the current would be like how fast people are going and how many people are passing a single location at any given point. So the current would be like how many students are running past the PE teacher who's standing on the side, timing people. And then the voltage would be like height differences. So actually, this probably isn't a great example for the track because the track doesn't have a height difference. There's not a whole lot of voltage. So what we'd really need to be doing is circuits around, say, Mount Burdell, where you're climbing up Mount Burdell and then coming back down Mount Burdell. And if there's lots and lots of pathways, then you could have 2 parallel pathways and people could go on 2 pathways together. If there's only 1 pathway, then everybody's on the same pathway. And then the resistance would be like rocks that you're running into or trees that are in the way that are slowing everybody down as they're coming down Mount Burdell, down to the bottom, and then they're taking a big gondola back up to the top again, and then coming down. If Mount Burdell were, say, a mountain bike raceway. That one's not as good of a example. Let's use the pipes, waterfall, water slides version. All right, so that is voltage, resistance, and current. It's hopefully a useful model for understanding how those things work. Make sure you've added those 7 concepts to your physics everything sheet, because we are now going to start using them as you set up some circuits and calculate some resistance, calculate voltage, calculate current, using a voltmeter and an ammeter. Have fun!